Dear students, last time we have discussed the geometrical isomerism in coordination compounds. Let us see today optical or mirror image isomerism in 4 coordinated as well as 6 coordinated complexes. Before that, we have to discuss what is meant by optical activity. So, optical activity, it is the property of a complex to rotate the plane of polarized light passing through it is called its optical activity, and the complex possessing this property is called as optically active compound. There are two forms of this optical activity or compound. The compounds which shows optical activity, these are divided into two forms. First one is dextrorotatory or called as D form. What are these? It rotates the plane of polarized light towards right, or we can say in clockwise direction. Second form is called as levorotatory or L form. This rotates the plane of polarized light towards left or in anti-clockwise direction. These D and L isomers are mirror images of one another. This is very important. For example, palm of our left hand and right hand. We know that these are mirror images of each other, and hence we say that these are the these D and L isomers, these are also called as enantiomorphs of one another. These isomers have same physical and chemical properties. Only they differ in direction in which they rotate plane of polarized light. Just we have discussed, D form rotates the plane of polarized light towards clockwise direction, while L form rotates the plane of polarized light towards left hand direction. Now what is meant by optical isomerism? The two compounds having similar formula but possessing such an arrangement of groups of atoms in a space around the metal ion such that one structure is the mirror image of the other. Got it? So one structure is mirror image of other, and very important is that these are not superimposable. That means when they are placed one over other, these are different. So these are called as optical isomers, and this phenomenon is called as optical isomerism, or it is also called as enantiomer. Let us see optical isomerism in complexes coordination number 4. That means to the metal ion 4 ligands are attached. In these complexes, types Ma4, Ma3b and Mab3 in square planar and tetrahedral complexes do not show such type of isomerism. Why? Because all arrangements of ligand around central metal ion is equivalent. So this is very important. Types Ma4, Ma3b, Mab3 in square planar and tetrahedral complexes do not show optical isomerism. However, in tetrahedral complexes, there are few cases in which ligands are not same. At that time, isolation of D and L forms is possible. In this type number 1, MABCD tetrahedral complex, all ligands are different. All ligands are not same. This type of tetrahedral complex gives D and L form. This is the example. To the arsenic, these 4 ligands are attached, and here these are the two isomers. Okay, one is D isomer, another is L isomer. Both are mirror image of each other. So see here, this is sulfur attached to arsenic. This is C6H4COO minus. This is C2H5. This is CH3. Here mirror is placed. So what happened? There is no change in position of sulfur as well as C2H5, but this CH3 is transferred to its opposite side due to this mirror, as well as the C6H4COO minus. This is also transferred to its opposite side. And when these two isomers are placed one over other, what happened? They are not superimposable. That means they are not same. That means this complex shows optical activity. In case of tetrahedral complex, this is the second type, MAB2, where this AB is called as asymmetric ligand. Both ligands are different. So MAB2 type containing asymmetric tetrahedral complex. Example is bis benzoyl acetanoato beryllium second. Here see, to the beryllium these two ligands are attached. Here also same structure is written, but what is the difference? Here mirror is placed in between these two isomers. Here this CH3 is above the plane, this CH3 is below the plane. Similarly, this is C6H6 is below the plane, this is above the plane. Same, this is above the plane while CH3 is above the plane. In this case, CH3 is below the plane, C6H6 is above the plane. Okay, got it. That means when these two isomers are placed one over other, at that time they are not superimposable. So therefore, these two isomers show the optical activity. Second reason is that this complex has no center or plane of symmetry. As we have discussed, their position in plane is different, therefore there is no center or plane of symmetry. Mirror images are not superimposable, just we have discussed this. But complexes of type MAA2, if the two joining atoms of this ligand are same, at that time they are not optically active. Only AB2, okay, joining attached atoms are different. At that time, what happened? These complexes show optical activity. Then see optical isomerism in square planar complexes. This is the compound which show the optical activity in all ligands and metal lie in the same plane. Therefore, it possesses planar center of symmetry. Hence, these complexes do not show optical isomerism. That means square planar complexes. In that case, what happened? Ligands and metal ion, they are lie in same plane. Therefore, they possesses planar center of symmetry. Hence, square planar complexes do not show optical isomerism. Only isobutylene diamine, mesostilbene diamine, platinum second chloride shows optical activity which has no plane or center of symmetry, and its structure is shown in above figure. This is the compound isobutylene diamine, mesostilbene diamine, platinum second chloride, which not have plane or center of symmetry, and therefore only this square planar complex show optical activity, while other complexes do not show such type of optical activity. Again I repeat, because they possesses plane or center of symmetry. Let's see optical isomerism in octahedral complexes. That means 6 ligands are attached to metal ion, and hence coordination number of metal ion is 6. In this case, type number 1, octahedral complexes containing only monodentate ligand. The ligand which donate only one lone pair of electron to central metal ion, they are called as monodentate ligand. In this case, type number 1, Ma2B2C2, 3 types of monodentate ligand. They are attached to the central metal ion. See here, this is the metal ion. At first position B atom, at second position B atom, at third and sixth position C atom. Then this is fourth and fifth position. Here there is A atom. Mirror is placed, and we say that there is a shift of A ligand as well as B ligand as well as again A and C ligand, and this position of B and C remains as it is. Okay, so B ligand from second position it is transferred to fifth position. Here C ligand is transferred from third position to fifth position. Okay, so these isomers are not superimposable and hence they show optical activity. For example, see here, this is PTNH3 twice Cl2PY2. So to the platinum, two ammonia groups are attached, two chloride groups are attached, two pyridine groups are attached. If mirror is placed, we found that this NH3 group is shifted to its opposite side. Similarly, these chloride atoms from second and third position shifted to fifth and fourth position, while the position of NH3 and pyridine remains as it is. If we place these two isomers one over other, it is found that they are not superimposable and shows optical activity. This is the another example. Cobalt is joined to two ammonia groups, two chloride ions and two NO2 ions. Okay, and in this way this compound is also shows optical activity. Then see next type of this type, MABCDEF. All ligands are different, so we say that bromide, NO2, NH3, iodide, chloride and pyridine. These are attached to platinum. Here mirror is placed and hence this is the mirror image of this isomer. These two images are not superimposable. When we place this isomer on this isomer, we found that they are not same, they are different, and hence this also shows optical activity. Now see type number 2, octahedral complexes containing only symmetrical bidentate ligand. Bidentate ligand is present, that means these are AA type of the ligand, that means two donor atoms from that ligand molecules are same. For example, see here, to the cobalt ethylene diamine is attached. Three molecules of ethylene diamine are attached. We know that ethylene diamine molecule contains two nitrogen atom donor atoms. Two nitrogen donor atoms. Here also these are present, two nitrogen donor atoms. Here also two nitrogen donor atoms. Mirror is placed. What happened? The position of these two nitrogen donor atom is changed. Now this nitrogen atom which is present at second position is shifted to fifth position. Followed. And this ring which is present at fourth and fifth position, it is now transferred to second and third position. Similarly, the ring which is present here at third and sixth position is transferred to fourth and sixth position. So in this way, these two isomers are also not superimposable and hence shows optical activity. Same structure is written here. This is the another example, optical isomer of chromium which is attached to oxalate ion. See here, oxygen, 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 oxygen. If a mirror is placed in between these two isomers, there is change in position of this attached oxygen atom. These two oxygen atoms which are present at first and sixth position, they are remains as it is, but there is change in position of second position. Now it is transferred to fifth position. Similarly, the oxygen atoms which are present at fourth and fifth position, they are now transferred to second and third position. Similarly, the oxygen atoms from this oxalate group which are present at third and sixth, they are transferred to fourth and sixth. Got it? So in this way, these are also not superimposable and hence shows optical activity. Then see next type in this category, MAA2BB, that means two types of bidentate symmetrical ligands are attached to metal ion, AA and BB. See this example, to the cobalt ethylene diamine as well as one oxalate ion is attached, and therefore see this structure. Cobalt is attached to one ethylene diamine molecule, second ethylene diamine molecule, and this is the third one, but it is oxalate. Okay, symmetrical ligand. So oxalate is also symmetrical, ethylene diamine is also symmetrical. This is also symmetrical because two nitrogen atoms are present which are same. In this case also two nitrogen atoms, two donor atoms are same. In this case oxalate, we know that first oxygen, second oxygen, donor atoms are same. Now when mirror is placed, what happens? This nitrogen atom which is present at second position is transferred to fifth position. Okay, and oxalate ion which is attached here at fourth and fifth position now transfer to second and third position. Okay, now this is the position of oxygen atom. Similarly, nitrogen which are present in this ethylene diamine molecule at third and sixth position now transfer to fourth and sixth position. So in this way, these two isomers when placed one over other, they are not superimposable, they are different one, and in this way it shows the optical activity. Now see type number third, octahedral complexes containing monodentate and symmetrical bidentate ligand. So this complex contains monodentate ligand and symmetrical bidentate ligand. For example, AA symmetrical bidentate ligand and B is nothing but monodentate ligand. For example, see to this cobalt, two ethylene diamine molecules are attached as well as two chloride ions are attached which are monodentate ligand. This is the structure. So cobalt, two ethylene diamine molecule. This is first ethylene diamine molecule. This is second ethylene diamine molecule which are attached to cobalt through two nitrogen atoms. And to this cobalt, two monodentate ligand, that means two chloride ions are attached. Mirror is placed. What happened? There is change in position of chloride ions which are present at second and third position. Now they are shifted to fourth and fifth position. Similarly, there is change in position of ring. See now, this is the position of two ethylene diamine molecule rings. In this way, these structures are also not superimposable when they are placed one over other. So this is the compound which shows optical activity. Now see this one, second type MAA2BC. Again, in this complex, a symmetrical bidentate ligand is present AA, but two types of monodentate ligands are present B and C. Example, COEN2, Cl and NH3. Two types of monodentate ligand, chloride and ammonia. See, this is the structure. Cobalt is attached to ammonia and chloride ion and two same bidentate ligand, ethylene diamine. When mirror is placed, so there is change in position of chloride ion. From second position, it is transferred to fifth position. Ethylene diamine ring is transferred from this position to its opposite position. Okay, due to mirror. Similarly, here this ethylene diamine from third, sixth, it is transferred to fourth to sixth position. These isomers again not superimposable, and in this way these two compounds again show the optical activity. Then see last type of the octahedral complexes which show optical activity, type 4, octahedral complexes containing optically active bidentate unsymmetrical ligands. So here listen carefully, this bidentate ligand is of type unsymmetrical, that means donor atoms are different. Here see, this is ethylene diamine molecule, this is 1,2-propane diamine, PN. Two donor atoms are different in this case, NO2. Okay, so different ligands are attached to cobalt. See this structure, cobalt is attached to two NO2 ions. This is 1,2-propane diamine. This is ethylene diamine. So when mirror is placed, there is change in position of NO2 group in this way. Now the NO2 which is present at second position is transferred to fifth position. There is change in position of ethylene diamine from fourth and fifth position. It is transferred to second and third position. Similarly, PN 1,2-propane diamine from third and sixth position, it is transferred to fourth and sixth position. When these isomers are placed one over other, we found that they are not superimposable, they are different structure, and in this way this compound shows optical activity. So friends, today we have discussed what is optical activity, what is optical isomerism, and the optical isomerism in coordination number 4 complexes, tetrahedral and square planar complexes. Remember well, in square planar complexes there is only one coordination compound which shows optical activity. And then we have discussed the optical isomerism in octahedral complexes, that means the complexes which shows coordination number 6. There are 4 types in this case in octahedral complexes, so that we have discussed in detail. So we stop here. In next lecture we start new topic, that is Pauling's valence bond theory. Thank you.